So, chapter 13. We're still electrophilic addition to pi bonds. But remember, we can't use aromatic bonds like benzene rings. They will not undergo electrophilic addition. Now we're going to look at types of bonds that have an intermediate or transition state through a ring structures. Okay, well, there's the outline. Okay. In the primary difference between the reactions we studied in chapter 12, and the ones we're going to study in chapter 13 is that in chapter 12, transition states had carbocation. So it took 2 steps at least to get to where you were going. But in chapter 13, we're going to look at reactions that proceed through a cyclic structure, primarily cyclopropane type structures. And what that allows us to do is to go through at least one fewer step. We don't go through a carbocation step. So the possibility of rearrangements are lessened. And well, it's just another way of explaining different reactions. You know, I've often thought about that. You know, what's so special about organic chemistry? Perhaps I should talk to an organic chemist to find out what they think it is. But from my point of view, it's like most other sciences. You study phenomena and then you try to explain it. So this is the way the organic chemists explain the phenomena that they actually observe. And then if you've, with experience and training and developing new theories, hopefully you're able to use what you know to predict the outcomes. That's what I'm really bad at right now, is predicting using what we know. Okay. So the formation of a carbocation is generally considered to be unfavorable simply because the carbon loses its octet. So there are 2 ways of approaching that problem. One is to understand that when you strip an octet from a carbon, that's going to be the slow step in any sequence of reactions. In other words, that's the bottleneck. So that'll determine the rate. And the fact that it's unfavorable means that you've got to adjust the conditions to make it as favorable as possible if you want that type of reaction to proceed. In this chapter, we're going to look at electrophilic additions in which the electrophilic atom has a lone pair of electrons. Then the addition can take place in a way that avoids losing an octet. That lone pair then satisfies the octet need for one of the carbons. But in order to do that, you've got to actually form 2 bonds at the same time. One bond to quench the octet for one carbon, and the other bond to be the electron pair donor from the pi bond. It'll make more sense when we look at the mechanism. Okay, let's see. We're going to look at, might have to be on the next slide, I think. We've generalized things. So let's just skip that and go to the next thing. Okay. So in this first step, well, actually, we're drawing a contrast here between the formation of a carbocation and the mechanisms that we're going to look at in chapter 13. So when we saw the addition of a Bronsted acid to this pi bond, the hydrogen formed a bond with one carbon, and then the carbocation resided on the neighboring carbon. And that was generally a carbon that would be more likely to stabilize the carbocation. The more highly alkyl substituted carbon would be the preferable one. But when we have an electrophile attacking the, well, actually, that's not the right terminology. When we have an electrophilic addition approaching a pi bond, I think we look at it first as the pi bond electrons attacking the electrophile. And then in order to avoid exceeding the octet on the electrophile, it donates a pair to the other carbon. So we form this ring structure, in which case all the atoms in the structure have their octets. Of course, it's obvious that depending on what that E is, you're straining bonds, right? Especially on the carbons. Because what's the ideal for a tetrahedral sp3 carbon is 109.5 degrees, right? And you can see that the bond angle for that CCE is 60 degrees. So there's quite a strain there. Which, by the way, also makes it extremely reactive. So the second step will proceed really fast. All right. So a word about stereochemistry. Since the molecule is planar, in other words, that R1 and R3 on that first structure are pointing toward the back, and R2 and R4 pointing toward the front. They're all in the same plane. So that electrophile can attack from one side, or it can go underneath and attack from the other side. So that gives you the opportunity to produce, in some cases, a racemic mixture of two enantiomers. But when you do that, the R1 and R3 are still in their same relative positions, right? They're still back pointing to each other, and the R2 and R4 are still pointing forward. Except that now you've got another body on the other side that is going to lead to, it has potential to lead to chiral centers on those carbons. Okay, this is a better way of saying it. The cis-trans relationship in the alkene is conserved. In other words, if R2 and R4 are cis to each other and R2 and R3 are trans to each other, they stay that way after the reaction. If the cyclic product is chiral, I don't know how a cyclic product would be chiral. I thought you had to have 4 groups. Well, no, actually chiral means handedness. So if one is the mirror image of the other, then you have a chiral center. Then you'll get stereoisomers produced. If the original alkene and other reagents are achiral, in other words, there are no chiral centers anywhere in that molecule. So I assume that R1, 2, 3, and 4, they could also potentially have chiral centers in them somewhere. But if they're not chiral centers, and the double bond, of course, is not chiral in that respect, then a racemic mixture is produced. If you do have chiral centers anywhere else in that molecule, then you get an uneven distribution of enantiomers. In fact, you may have diastereomers, more than likely, because you're only changing one or two chiral centers. And if you don't flip, everybody flips the opposite direction from one to the other, then you don't have enantiomers. You have diastereomers. Okay. One way to form this cyclic structure is through the use of an electrophile called a carbene. A carbene is simply a carbon with two groups out here, whatever they happen to be, and a lone pair. So if you run the, if you calculate the, let's see, hold on a second. If you calculate the formal charge on carbon, right, you got one from here, that's two. You got two from here, right? And then what is carbon's valence number is 4, okay? So 4 minus 4 is equal to 0. So there's no charge on that carbon. This is an uncharged species. And the model on the right there is of an sp2 hybridized carbon with 2 free p orbitals. Now it has it's neutral charge, it's 0 charge, but it's still missing its octet. It only has 2, 4, 6. So it's octet, it's electron deficient in that respect. Okay, so that makes it the electrophile. It's looking for electrons. Okay, and the species with the pi bond is the nucleophile. It's the electron-rich species. So it's going to do the attacking first, the pi bond. All right. Since carbenes are extremely reactive, they have to be generated in the reaction mixture. In other words, you can't buy them off the shelf from a supplier, right? I'm sure they've tried, but they found out pretty quick that it doesn't work, because if you have pure carbene in a bottle, it's going to react with its neighbors. So in this case, we want to react the pi bond that's not aromatic, right? So you see you've got 2 aromatic rings there, 2 benzene rings. They're not going to react at all. So you don't even have to worry about them. The only one that's going to react in this case is that single, that terminal pi bond, right? And one way to form the carbene is with diazomethane. Right. So it's going to look something like this. This, and this is going to be slightly negative. This is going to be slightly positive. And this is a very, very weak bond. Let's see, I think I need 2 over there. So when this bond breaks, I don't have enough. Well, yeah, it says I do. I do have enough. Let's see. I think we got a better. Yeah. Diazomethane is precursor. I don't chapter 12. Did we talk about green chemistry in chapter 12?
Yeah.
Okay, so this is one of those that you want to be careful with. Diazomethane is explosive. In other words, it decomposes rapidly and gives off, it's an exothermic reaction. So there are other ways to make carbenes that are more stable. This is where we start our discussion of carbenes. This is a pure. All you need is a carbon with one lone pair of electrons. That's a carbene. So it can be attached to almost anything. That H looks like a V is a nu. Right? Let's see. I think that might have been in first semester we covered that. H nu. This is the Greek letter nu, which stands for frequency. The frequency of light. This is Planck's constant. That's equal to the energy of a photon. We didn't talk about that in 102, did we? Okay, so I covered it in 101.
Or at least not yet.
No, I don't think we're going to get to that. So what this means is you shine a light of a certain wavelength and it breaks that bond. It's probably ultraviolet. Ultraviolet light shine on this, and sometimes you do like that. And it will break that bond, and that will form nitrogen and our carbene. And then the carbene can react with that double bond. That's convenient, actually. So if you got your mixture, you put your mixture together, and all you need is a window, and you just shine your UV through the window and set the reaction going. So when you, oh, I got it backwards, sorry. What happens is these electrons go over here, and oh, this one's already got a lone pair on it, sorry. So that's 2, 4, 6, 8. Okay, yeah. This carbon has an octet already. So we're going to deprive it of its octet by these 2 electrons going to that nitrogen. Now they're over here, and this is our electron deficient carbene. And then it forms that cyclic structure. Yep, and it's explosive. I'm not sure what concentrations you need to use of this stuff in order to produce the reaction, but if they're cautioning us against explosive possibilities, it's probably relatively high concentration. Let's see. Okay, I've already talked about that. What happens to it? Step 1. Oh, that's a heterolysis. Yeah, both electrons from that bond go to the nitrogen. That's a heterolysis step. And then you get the carbene reacting with the pi bond is the electrophilic addition step. But then you can do stuff with that 3-carbon ring. Right? You can add stuff to it. All right. So here's another possibility for a carbene. This MCPBA, that's metachloro per benzoic acid. Metachloro per benzoic acid. So the chlorine and the oxygen group on the right, they're in the meta position. Remember when we were talking about our nomenclature? If you have this one occupied with something, if this one is occupied, that's ortho. If this one's occupied, that's meta.
And then pair.
And then pair is this one. Yeah. So The effect of this metachlorobenzoic acid is to it's a simplified version for the mechanism. And we form the ring, not with a carbene this time, but with an oxygen from that MCPBA. So it's like reacting, let's see, we have this one, what is that, a 5-membered ring? Yeah, 5-membered. There, like that. It's as if we have an octet pour, right? Octet pour oxygen. So oxygen is 6, so it's a 0 charge too. I mean, this is to simplify the mechanism so we can understand it. But the reaction itself takes place with that whole MCPBA. And it produces this ring structure here. Like that. So what happens is, right, electrons transferred there, and then these electrons go to there and form that bond. So you get 2 bonds forming simultaneously. If we have this trans-but-2-ene, if we form a cyclic compound there, then what we're going to end up with is a well, let me see. It's an epoxide. Yeah, right. This is what's known as epoxide.
So the oxygen.
Oxyrain. Yeah.
Yeah.
Yep. I don't know if we could. Oxyrain is really like that. That's oxyrain.
Yeah.
So it's similar to that. An epoxide is broader. It covers more possibilities. So let's see. What happens with those 2 products, those trans-but-2-ene oxide? It could attack from one side or from the other, and it gives us those 2 possibilities. Now, if we take one of them and try to superimpose it on the other, we can't. Right? Those are enantiomers, aren't they? Right? If you take one and flip it over, try to lay it on top of the other one, right? Now if it was this way, yeah, if it was this way and this way, you flipped it over, then if you flipped it over, oh, wait a minute. Well, if you flipped it over, then it would be this one back and that one forward. Okay, so they're not superimposable. They are enantiomers. All right. Now this is 1 peroxy acid. What do we mean by that? Well, if you have an R group here of some kind, and in this case we have the chlorinated phenyl group, but it could be anything. And then you have your carbon here and like that. If we just did this, that would be a carboxylic acid. But instead, we stick an oxygen between. And that makes it more reactive. But the product is the carboxylic acid. Right? It gives up an oxygen in this process. Okay. The advantage to this is that very mild conditions are required to produce an epoxide. And many alkenes are common or easily synthesized. Oh, I see what you mean. Okay, if you want an epoxide of a certain type, the alkene that can be reacted with this peroxy acid are sky's the limit. Right? It's easy to manufacture the precursor. So this method is very useful. We're still conserving the stereochemistry. In other words, one methyl group from that trans-butene is on one side, the other methyl group's on the other side, and if it attacks from below, you get, or from the other side, they're still opposite one another. They're trans. Or E. E and trans are synonymous in this case. All right. So here's the actual mechanism for the MCPBA reaction with our pi bond to form the epoxide. In order to get that oxygen away from the peroxy acid, you have a ring structure. You have this oxygen here, and then you have this oxygen here. But you also have another oxygen down here, and then a hydrogen here. Well, remember what is required for a hydrogen bond. You need oxygen. You need either oxygen or nitrogen or fluorine. Yeah. And hydrogen. Well, it doesn't have to be on the other molecule. It can be on the same molecule. So we set up a hydrogen bond there. And what that does is it weakens this bond right here. It starts pulling this way and weakens that bond. This bond is inherently weak just because it's a peroxide. So with these bonds both weakened, now we can get that oxygen off of there. So when the double bond comes into play, it attacks the oxygen. Let's see. Let's account for all of our electrons. And then this attacks there. And then, of course, to retain the octet, and this bond gives breaks. That bond forms. This bond breaks. And we get these two bonds to give us the epoxide. So that's actually what happens. And whereas the alcohol group was on this side of the molecule in the beginning, now it's on that side. I left out some arrows, didn't I? Actually, we're breaking a rule here.
Yeah, there's more than 3.
Uh-huh. Okay. Well, who says that that's a hard and fast rule? Only David Van Vranken says so. But he's just one person.
Yeah.
Whatever it takes to explain the reaction. That's the thing we're after. Okay, so we've got our and this all takes place in a single step. So we got electrons moving everywhere. It avoids the carbocation formation. That's good. And you don't have to worry about rearrangements, right? Hydride shifts or methyl shifts. Let's see, we get the oxygen transferred. Mentions the inherently weak bond here, and then the weakened bond here from the hydrogen bonding formation. And since it takes place in one step, we retain stereochemistry. The relationship of any of the other bonded groups on that the pi bond carbons are preserved. That can be useful. Okay. And here's the alternate explanation where you actually just separate this oxygen out with 3 pairs of electrons, and then you proceed through. This is a simplified version. It's not reality, but it's what we do in mechanisms to simplify things. All right, identify the missing compound A and C for each one of these. All right, excuse me. So if we use concentrated phosphoric acid on a cyclohexanol, what is it going to do? It's going to form a double bond, right? So it's going to form cyclohexanol. It's going to form a product like this. That. And then MCPBA in dichloromethane will form this product. Oops, wrong way. You draw that bigger. It'll form this product right here. And then we can use base and water to do what? I don't know if we talked about that one. That doesn't look familiar. Does that look familiar to you? No. But
I
what
guess they expect us just to know it.
no, it's got to be presented somewhere. So if we've got water out here, under basic conditions, excuse me. You see, are they going to show us what it is? No, they're not. Okay, I got it right up to that point, but I was stumped from here to here. And then the enantiomer, it'll also be this. For both of those products, depending on. So what that tells me is that I think we're going through a carbocation step because we can attack from both sides. So if this has got 2, 4, 6, 8. It's one of these carbons, either of these carbons should be electron deficient. So this is going to attack no, it's going to be the oxygen. Deprotonates that. Deprotonates that. And then now I'm grasping at straws. I can't explain it right now. I bet we'll get to one of those when we do the review. Let's see. So now we're going to take molecular bromine, actually molecular halide of any kind. Didn't we do that in chapter 12?
Mm,
Molecular, yeah, molecular halides reacting with,
Yeah,
yeah, we did. Okay, so so we're gonna get a carbocation. Yeah. We're gonna get a carbocation, which means we can attack from either side. All right, this is the generalized takeaway. Whenever you get and this is in an aprotic solvent, right? Carbon tetrachloride. Well, they call it tetrachloromethane. We get addition of bromines, both bromines from that Br2, across that double bond, one from the front and one from the back. That means we get two possible isomers, trans isomers. Now, why is that? That's only 59%. So what happened to the other 41%? Okay, like carbines and peroxy acids, molecular halogens such as dichlorine, I forgot to subscript those, such as chlorine and bromine can react with an alkene to produce a three-membered ring. Okay. All right, so what does that look like? We get a racemic mixture of this trans 1,2-dibromocyclohexane. Maybe they're just saying it's 59% efficient. But there's got to be something else. What, I mean, do we have reactants left over? It's possible. All right, so bromine, dibromine, dichlorine, they're non-polar, right? Normally. But when they approach that pi bond with those extra electrons sitting out there, then that induces a dipole, an induced dipole. And it repels electrons away to the other side and makes one side positive. Now we have one of the bromines is electron poor. So the pi bonds from the double bond of the two carbons can act as a nucleophile. It can attack that bromine because it's slightly positive. All right. So that's what it does. Right? It attacks that bromine. Yeah, the pi bond attacks one bromine, and to maintain the octet, it forms a bond with the other carbon. So we get a three atom ring structure with bromine on one side, but the bromine has only 1, 2, 3, 4, 5, 6, has 6 electrons, and it normally has 7, right? -6. So it has a positive formal charge. Okay. So since it has a positive formal charge, the bromine that's left behind with its negative charge will attack one of those carbons. And the bond will break to preserve one of the bonds of the ring structure will break easily because it's very strained. Will break easily, and the homolysis of that bond will transfer those electrons to the bromine that's already attached. And that's why they're always opposite to one another. Right? It can't approach from the ring side. It has to approach from the other side. So that makes them opposite one another. They're trans. Okay. That's an SN2 reaction? Yeah, that's an SN2 reaction. The bromonium ion is an intermediate with with the electrophilic addition step. Then the SN2 completes it. All right. Let's see. I should have been clicking my mouse. The mechanism must not proceed through a carbocation intermediate. Otherwise, both syn and anti additions would take place. Right? So we don't get a syn addition. Syn's from the same side, anti is from the opposite side. So we get an anti addition, which gives us the trans relationship, or the anti relationship of the bromines. But of course, the bromonium ion can form from the other side too. So that would give us bromine on the other side. So you can have from your double bond, you can have a bromine on this side and a bromine on this side. Or if it attacks from the other side, you can have bromine over here and bromine over here. Just depends on where the bromonium ion starts. That determines the isotope, not the isotope, the isomer, excuse me. Okay. All right, so there it is in black and white. Hopefully, I followed those steps. I need to be clicking my mouse to do this. All right, so here we have an ether and an ene. And with bromine, we're going to add across that. We're going to create a bromonium ion across that 2-ene. All right, these are what we would expect the outcome to be. It's going to leave that ether alone. In fact, wasn't that one of the methods of protecting groups is to form ethers? Yeah, form ethers and protect. So who knows where that came from, or whether it was a precursor already there. So these product molecules, since we have a chiral center over there by that one methyl group next to the ether, we already have a chiral center. That chiral center doesn't change. So now, instead of producing enantiomers, we produce diastereomers. They're not mirror images of one of them, is what I mean. Okay, so here's a trans-butene, and we're going to chlorinate it across that bond. And it follows the same mechanism as we described for the bromine. Instead of the bromonium ion, it forms a chloronium ion as an intermediate. And we get a meso compound, which is, it says, I stuck that achiral in there to remind me. The meso mixture is achiral. That is, it does not rotate polarized light, because you've got one rotating one way and another one rotating the other way in equal amounts. Actually, meso compounds are not enantiomers, I don't think. And it's probably because that molecule is symmetrical. In other words, when we go like this, this, and this, like that, our plane of symmetry would be there, and all we have to do is flip it, and it looks just like the other one. Okay, so this chlorine undergoes addition to alkenes and produces these vicinal dichlorides, which means they're on neighboring carbons. That's all that means. We can do this with fluorine and iodine also. although they're not as commonly used. The fluorine reacts explosively with alkenes. Right? The reaction is just too violent. I mean, if you actually need it, then you have to take special precautions. You may have to conduct the reaction at lower temperatures and just wait longer.
So how would that make it green now? Like it wouldn't then, would it?
No, not to use fluorine. No,
'Cause that's why I was like, we were talking about green, and then you said that that one was explosive.
Yeah.
So I was like, what? That wouldn't be green.
No, green would be the other.
Yeah, the
Go
opposite.
away from it. Yeah, right. The reaction with iodine is energetically unfavorable. So it must have a huge activation energy. All right. Now, what do we do if we're faced with an alkyne? If we have one equivalent of bromine, excuse me, I got to get this thing out of my way. When we have an alkyne and we adjust our ratios so that we only have one equivalent of bromine. In other words, we only have two bromines available. Then we generally get a 1,2 substituted and across one of the pi bonds, and that leaves a double bond behind. But notice that the stereochemistry flips from anti to syn. You have both products. So we have to look at the mechanism to see why. Now, if you have bromine in excess, it's going to go in there and brominate that other pi bond as well. So the way you control how much bromine is added is with the ratios. Right? I assume that if you just get close to one equivalent of bromine, because right, I've already, well, since you didn't take 101, I may not have told you this, but when you're reacting, say, two reactants to yield some products, whatever, then you have absolute amounts of both of them. One of them is going to be limiting because there's always enough error so that you can't get exactly stoichiometric mixtures. There's no way. So one of them is going to be limiting. That's a general chemical rule. But apparently, in organic chemistry, if you get close to one equivalent of bromine for one equivalent of oct-1-ine, then you can expect to have just the di-substituted bromine compound. Then if you put in excess, of course, you're going to get you're going to brominate the other pi bond as well. Now, here's the mechanism coming up, I think. Let's see. You're going to get two possibilities. An alkyne will produce a syn and an anti-addition. And you control the formation of the di-substituted versus the quatro-substituted with the ratio of the halogens. Two equivalents or excess will give you tetra-substituted halogen. Okay. The electrophilic addition of bromine to an alkyne does not proceed through the bromonium ion. The reason for that is the sp2 hybridized carbon atoms would be too highly strained in the ring. In other words, sp2 hybridized carbons are going to be trigonal planar. And well, I'm going to take his word for it. The bond strain is too high. So we don't proceed through that mechanism. Right? So we need a different mechanism to account for the additions and for the difference in stereochemistry. Right, for this cyclohexene, oh, wait a minute. I thought we were going to get a mechanism for that. Looking. No? Okay. Well, maybe the mechanism is too complicated. All right, so I guess we're just going to have to memorize the fact that stereochemistry is not preserved. Right? Well, on this terminal alkyne, you don't have any stereochemistry because you got two hydrogens out there. Right? So you could get bromine trans or bromine cis, either one. The trans seems to be the more favorable one, probably because of steric hindrance. Right? You get two bromines on the same side, they're going to get in each other's way. All right, I guess we're going to have to leave it there. So, in aprotic solvents, like carbon tetrachloride, you simply add both bromines across that double bond. If you conduct the reaction in a protic solvent like water, well, it has to be a protic solvent to yield a halohydrin. Rather than two bromines cross, you're going to get a bromine and a hydroxyl. So you're going to get an alcohol and then the bromine substituted across those two carbons. But we're still stereospecific. So that means we still do proceed through a bromonium ion in this case, or a chloronium ion in the second case down below. We preserve the stereochemistry. All right, so there's your bromonium ion. And now since we're in an aqueous solution, the bromide ion is present, but water is a better nucleophile. Simply because it's in greater abundance. Right? You just got too much water there. The competition is, the water overwhelms their bromide ion with its presence. So instead, the oxygen attacks the one of those carbons, and that breaks the bond and releases the bromine from its three-ring cycle. And now you've got water attached, and now you need to deprotonate. So one of those protons from that attached water transfers to another water molecule. And now you have your formed in an anti-arrangement. So there's also regiochemistry that has to be considered when we're forming halohydrins. The major product is going to be the one where the alcohol is placed on the more stable carbon. So in this case, the more stable carbon is closer to the phenyl ring. So the regiochemistry gives us an unsymmetrical production. We get 78% in this case. The major product where the hydroxyl is on this number 2 carbon. And the minor product puts it on the other one. So you still get the two possibilities, except it's uneven. It's unsymmetrical. So here's why that happens. When you form the bromonium ion, in this case, which is the weaker bond? Well, the carbon that's closest to the phenyl ring is more positive in its charge. So that's the one that water attacks. It's more positive because the phenyl ring in its electron distribution. It's forgot the term. It's not coming to me. Anyway, when you have those double bonds, the electronegativity, the effective electronegativity of that phenyl ring is higher than it is for single bonded carbons. So there's an electron withdrawing effect on, we can't blame it on bromine because bromine is drawing equally from both carbons. But we can blame it on the phenyl ring, is more electronegative, and it's making that carbon more positive. So the nucleophilic, the substitution, nucleophilic substitution occurs at that carbon in preference to the carbon that the other carbon, number 2 carbon. It still happens though. It's just not as common. Okay, so if we were to use a strong acid in a protic solvent like water, then we know from the last chapter, we go through a carbocation step, and the more stable carbocation in this case, let's see, if we have this is our precursor like that, then when the electrophilic addition occurs with hydrogen first, right? So we get a bond formed there, and then we get the chloride ion here, and this leads to that hydrogen there, and because now this carbon is deficient, right? Well, there's a hydrogen here also. Hydrogen there. But now this carbon is deficient. It's missing an octet. Okay. So where is it more stable? Right? We get a hydride shift. Right? We have these methyl groups here, and we also have a hydrogen here. So this hydrogen goes here like that. And now this one is positive. When this hydrogen comes over here, now this one is positive, and we have the hydrogen over there. This one is a more stable carbocation. So this 1,2 hydride shift gives us the more stable carbocation. Now that chloride attacks here. That's why you get that product rather than chloride attacking here. Now, this would be a minor product, but the major product would be that one. The 2-methyl-butyrol from a carbocation rearrangement. Now, what we're going to do is introduce a procedure that guarantees the formation of the hydroxide here with oxymercuration and reduction. Let's see. Hope I did that right. No, I didn't do that right. Did I? No. Boy, that was dumb. Now that we have, sorry. Now that we have our carbocation here, that up to that point we're okay. And so we have our hydrogen there. Up to this point, now we have water. That attacks here. And that gives us, because you need a good leaving group. So now we have the oxygen there, and this is positive. So now what we do is we do a proton transfer. Yes. Do a proton transfer, and that gives us the alcohol. Okay, sorry about that. I don't know why I did that. Now, we could do that in aprotic solvent, probably. But not when you have a strong Lewis acid in aqueous solution. Then this is what you get. All right, now back to the so okay, I should have followed along. So how do we guarantee that that hydroxyl resides on the number 2 carbon and not on the number 3 carbon? You know, that step may have been wrong too. It's an acid catalyst. So what it does is it makes hydronium ions. And I think the hydronium ions is what no. No, I think that was right. Okay. So this is called oxymercuration and reduction. So it takes 2 steps. We use this diacetyl mercury in water and tetrahydrofuran. Tetrahydrofurans. That's tetrahydrofuran. It's based upon furan, which is this. So you just add hydrogens across those double bonds. Now you have 4 extra hydrogens on there. That's all it is. And then you have to go through a reduction step. That's what the sodium borohydride is in ethanol. And that will give you the 1-2 relationship of the hydrogen added and the alcohol added across that double bond. Now here's why it works. Mercury is intimately involved here. We form a 3-ring structure with mercury and whatever else is attached to mercury, this acetyl group. So in order to do that, one of the bonds between the mercury and the oxygen breaks. And we're left with mercury in that 3-ring structure with an acetyl group attached to it. Then, since it's an aqueous solution, the water attacks the carbon that is more positive. And before I said phenyl groups are more electronegative. That's true. They do have a withdrawing effect, but so will methyl groups. They will also have a withdrawing effect. So the positive charge, the slight positive charge, is still on that carbon closest to the methyl groups. So that's the one that water attacks. And then we deprotonate it, and that leaves the hydroxyl group in the position we want it on the number 2 carbon. Now, the rest of it is a little more complicated, trying to get rid of that acetyl mercury group. We use sodium borohydride, which is a common reducing agent. And from those arrows, it takes 3 steps to get there. So we're not going to go into that much detail. Okay, so there's the explanation. It may appear to be a simple nucleophilic substitution reaction, actually proceeds through a more complex mechanism that's believed to involve radicals, species with unpaired electrons. Okay, so this is one of those where you're just going to have to take a lot of it on faith and just focus on the formation of the three-ring structure. Three-membered ring structure, not three rings, three-membered rings. Mercurinium ion. Okay. Say that 3 times fast. So since there's not a full positive charge on that on the carbon, then we don't get a rearrangement. And plus the ring structure prevents that from happening anyway. So how about syn or anti-addition using this method? Well, the problem is that the regiochemistry, the stereochemistry is preserved in the first step where we form the ring structure, the mercurinium ion. But the reduction step scrambles all that. So when that happens, now we get enantiomers. And in fact, we get 4 enantiomers. Right? We would get enantiomers if the stereochemistry were preserved on that double bond, then we would only get 2 enantiomers, assuming there were no other chiral centers involved. We get 2 enantiomers. But since the reduction steps scramble that, so now we have 2 enantiomers for each of the 2 that we would have gotten. So now we have 4 enantiomers. Because there are 2 chiral centers, that means we can have 4 possibilities, 4 combinations. So there is that. I mean, you get the hydroxides on the carbon you want it, but the stereochemistry is all messed up. So what happens if you use this procedure on alkynes? Well, here's an alkyne, 2,2-diphenyl pent-4 enal. That means you have an aldehyde there, and you also have an enal. You also have an ine. Now, okay, that's right. The aldehydes take precedence over the ines. All right, so the ine is relative to the carbon that's attached to the carbonyl group. So that'd be 1, 2, 3, 4. Yeah, okay, that makes sense now. And the 2 phenyl groups are on the number 2 carbons. Okay. If we use this procedure, what do we get from it? Well, apparently we get the alcohol group is on the carbon we expect. It's on the number 2 carbon, but we get an enol, and enols are very, very unstable. So it tautomerizes to a ketone. So the end result, and this tautomerization occurs so fast that you can't isolate them. So the enol tautomerizes to the keto form, which is more stable. So the long and the short is you don't get an alcohol, you get a ketone. And still it obeys the Markovnikov formula. In other words, the hydrogens added to the more hydrogen substituted carbon, which would be the terminal carbon in this case. Okay. I know this is taxing. We'll try to move along as fast as possible. Uh, so mercuric ketone. Oh, reduction with the sodium borohydride is not required to remove the mercury substituents. So that's why on that previous slide, I think, yeah, we didn't have to reduce it with sodium borohydride. That's good because now that preserves any of the stereochemistry that you had from the beginning. That's good news. It will automatically the mercuric acetate will automatically leave. Water is sufficient to hydrolyze. Okay. Ketones from alkynes. All right. So there's a phenylethyne. You get a phenylethanone. Right? You can use, actually, this is a different mercury catalyst, mercuric chloride. Or you can use mercuric sulfate. And you still get ketones. You don't get an aldehyde, which would be anti-Markovnikov. I'm wondering, what if you do want an aldehyde? There are other reactions you can use for that. Okay, internal alkynes. Right, that was a terminal alkyne. What happens to internal alkynes when you use this forgot my term, oxymercuration? Okay. They can also be converted to ketones, but you get a mixture of isomers of ketones. It looks like the 2 position ketone is favored over the 3 position, but you still get the 3 position. Now the mechanism is supposedly going to tell us why that is. No, it doesn't. Come on, Cardi. Right? You had a good thing going there with your mechanisms, and now you're leaving us hanging. So there must be the ability to break bonds on either side, right? To add the alcohol, form the enol, and then the enol will tautomerize to the ketone. And it depends on which side the enol is as to which ketone is formed. That's the way I look at it. Alkoxymercuration. All right, that was oxymercuration where we simply added an alcohol. If we use an alcohol instead of water, then we'll get an ether instead of an alcohol. We'll get an ether, but we still have to use reduction in this case. All right. All right, let's see what we got here. All right, we're going to use ethanol. Okay, instead of water, we're using ethanol. So we're going to get an ether. Now, where's that ether going to attach itself? This is a terminal alkene. So the ethanol should be on the number 2. We should get an ethoxy group. Okay. And this thing out of my way. It's not in your way, it's in my way. There it is. There's your shoot. What does this happen to me? There's your ethyl ether. And I assume since we're having to reduce it with sodium borohydride, that any stereochemistry you start with is just jumbled up. All right. How about hydroboration oxidation? So in this case, we're going to use boron trihydride, and tetrahydrofuran is the first step, and then hydrogen peroxide, basic hydrogen peroxide in the second step. This gives us an anti-Markovnikov regiochemistry. So it must act through a different mechanism in order to do that. So if you want the alcohol to be terminal on a terminal alkene, then use this rather than the previous examples. Okay, so far we've covered two reactions that serve to add water across carbon double bond or triple bond. Right, the acid catalyzed hydration, which proceeds through a carbocation. That was from chapter 12. Excuse me. And then oxymercuration reduction, which proceeds through a cyclic mercurinium ion intermediate, avoiding the carbocation rearrangement. Okay. Both of these reactions add water in a Markovnikov fashion. The OH group is the one that is better able to stabilize a positive charge. Okay, so either of these reactions is stereospecific. In each case, a mixture of stereoisomers from both syn and anti-addition is produced. Right, and that can be, and if it involves a sodium borohydride reduction, then you get all possible stereoisomers. It just mixes them all up. In this case, hydroboration and followed by oxidation adds hydrogen and hydroxyl to an alkene with an anti-Markovnikov regiochemistry. So there must be a different mechanism. Right? So get this out of my way for temporary. We have it's written like this. In other words, when we write the recipe for the reaction, we write it like that, but the mechanism takes place through through this, excuse me, diborane. And like that. So the ratio is still the same, like 1, 2, 3, 4, 5, 6, 2 there. So that's 1 to 3 or 2 to 6. Excuse me, not that one. So we say BH3, but it's actually B2H6. And to further complicate things, that's not even the species that reacts. The BH3, well, it would be this if it were just in aqueous solution. But if we add THF to it, tetrahydrofuran, now we form that borane THF complex. That's the one that reacts. Since borane is unstable, we stabilize it with tetrahydrofuran. Because BH3 is octet deficient. Remember that? Yeah. Yeah. Boron doesn't have an octet. It has a sextet. All right, so a more stable variation is actually sold commercially. How about that? 1-to-1 complex with tetrahydrofuran, where THF acts as a Lewis base, it donates electrons to stabilize the boron atom. All right. There are other possibilities. DMS, dimethyl sulfide, will also work. All right, so to simplify the mechanism, we leave the THF out of it, and we simply say that the boron is electron poor, and of course the alkene is the electron rich. And the attack comes from the pi bond, which attacks the boron, which is electron poor, starts to form a bond there, and then to maintain the octet on the other carbon, we have to start forming a bond with the hydrogen, one of the hydrogens. All right, so we get this temporary intermediate. And when the bond between the boron and the hydrogen breaks, then the bond between the BH2 and the H are complete. So now we've consumed that pi bond, but now in order to excuse me. I'm looking for, okay. We're going to get to it eventually. I was just questioning my slide set. So this happens to be regioselective because that step takes place, is a concerted step. In other words, take place all at once. Ah. There's a steric repulsion that we see with the well, when the borane adds to the alkene, the larger group BH2 to the carbon atom with a lesser number of alkyl groups where there is more room. So rather than the boron adding to the carbon with the extra alkyl group, like there, that's why they put that X in the way. It goes the other direction. So you are unlikely to form, or it's a minor product. You would form the boron on the side with, actually, this would be the Markovnikov addition. If you got the boron on the one with the methyl group. The anti-Markovnikov is the one that's preferred because of the steric repulsion. Boron, the borohydride prefers the other one, where it's further away from the methyl group. Okay. All right. Actually, it's pretty complex. You don't just form one boron, one borane, alkyl borane, then you form another alkyl borane with that same boron, then you form a trialkyl borane, and that replaces all the hydrogens with your substrates. Okay. Then you have to oxidize it. And instead of using sodium borohydride, we use hydrogen peroxide. And that produces the alcohol group from where the boron was situated. So that gives you the anti-Markovnikov, because the hydrogen now is on the less hydrogen substituted carbon. All right. There's more mechanism. I'm not going to stay here with this one because it's just too complex and takes too much time. This shows the oxidations using hydrogen peroxide. It has to happen several times because we formed a trialkyl borane. All right, what are we going to get out of this one? Well, let's see. The Markovnikov version would be what? Let's see. We got this is a fused ring system here. Fused on these two. So this is that. This one has the double bond on it right there. Okay. So the hydrogen addition would normally be on this one because 1, 2, 3, 4. There are no hydrogens here. Right? So we would expect the hydrogen to be here, but in fact, it's not. The hydrogen shows up here, and the alcohol is there. Oops. Okay. Yep. Oh, accounting for stereochemistry. All right, I didn't do that. So if we attack from one side, then both the hydrogen and the hydroxyl are going to be on the same side. Right. So they'll either be wedges or dashes. Both of them. That's why it says and the enantiomer. So that means both of them will be dashes. All right. How about alkynes? If we use hydroboration on alkynes, well, we're going to get the attack so that we get syn addition, right? And there are several steps to that mechanism, but we're going to end up with the borane on one side of the carbon and the hydrogen on the same side. And we get a mixture of products. Okay. Oh, good. They're going to show us. All right. Again, aha. So in this case, if we do it, if we want to use hydroboration for an alkyne, that's the way that we can get a terminal carbonyl or an aldehyde rather than a ketone, because we get an enol, and then the alcohol is converted to an aldehyde, and we lose the double bond on those two carbons. So that's how you get your aldehyde versus the ketone. All right. These are other types of boranes that are used. They're bulkier. So my guess is if you want a higher yield of the anti-Markovnikov, then you would use a more bulky group. Then you would preclude the Markovnikov option. All right. Organic syntheses. Okay. Now what Cardi's going to do, and we don't have to spend a lot of time on these because actually we're taking things in reverse. Notice that double shafted arrow. That's your organic synthesis arrow. So we went from right to left in all the previous slides, and now going to go left to right.
I mean, is it like,
I'm sorry?
does it really matter? Like when it comes down to it? Like what subject company?
No. It depends on where you start. If you know the product that you want, then you would use this way. And you would have to see if we wanted these groups on the same side here, these methyl groups on the same side of that molecule, then we would need a cis isomer to start with. And diazomethane would give us that product. All right. Let me see. Let me get this out of the way. There we go. Okay, so if we want to end up with a trans in this case across a double bond, then we would start with an alkene that was an E isomer. Let's see. A peroxy acid, conserving the stereochemistry in the process. Well, that would probably be safer too. MCPBA would be safer. Oh, that's an epoxide. The previous one was a carbon-carbon-carbon ring. Okay, my mistake. So we would use MCPBA to preserve the stereochemistry in this process. This is where we left off when earlier today we lost internet in our class on the Greenbrier campus. So I'm picking this up at home. And there are just a few slides left to finish out this lecture. And at this point, we've introduced topics that are electrophilic addition to nonpolar pi bonds using three-membered rings. So the main advantage to that then is to avoid the types of reactions we studied in chapter 12, which involved a carbocation. And very often, not always, but very often, what will happen is the stereochemistry of the substrate molecule will be preserved in this process. Whereas with a carbocation, it's a two-step process, and once the carbocation is formed, the attack can come from either side, which gives you a mixture of stereoisomers. All right. So we're at the point now where we're using these reactions that we have encountered in chapter 13. And we're looking at them in terms of synthesis. So that's why in each one of these examples, we see the double shafted arrow, which means we're working in a retrosynthesis mode. The product is on the left-hand side, and the potential reactant is on the right-hand side. And then, of course, on each of these arrows, we show what type of reaction is required to produce the product on the left-hand side. So that means in this case, if we have a bisphenol dihalide with the bromines in a trans configuration, then what we want to do is preserve. We want to add bromine across the double bond in such a way that we get a trans configuration for the bromine. We preserve the methyl group arrangement that we find in the substrate molecule, the alkene on the right. So you notice that the alkene is cis, right? These methyl groups are cis to one another, and they need to be cis in the product. So there's one there in the plane, and this one is pointing toward us. So in order to do that, we need a bromine addition across that bond. let's see, I'm not sure if I drew it that way. But it probably bears repeating. If we have the like that, and then we have the bromine like this. So each bromine atom has a and the molecular bromine is diatomic, and each of the bromines has an octet. And the electron rich is the double bond. The pi bond of the double bond is the electron rich. And the electron poor is the bromine. Of course, we showed earlier that bromine molecules are nonpolar, right? They don't have a permanent dipole. But as this bromine approaches that concentrated negative charge in this pi bond, it induces a slight positive charge on one side and a negative charge on the other. So now we have the electron poor side, and this attacks this one and forms a bromonium ion. So we get the formation here, and these electrons go over here. So now we have this bromine ion, and we'll form the bromonium ion here on one side of that double bond. It could be on this side, it could be on the other side. So either one of those bromines would satisfy, and it would give us the bromonium ion, which should be positive. Okay. Now that we have that ion, this bromine attacks the backside. So this bromine then would attack the carbon that's going to have the that is the most substituted with alkyls. That's because they tend to withdraw electron density away from this carbon. This is the more positive side. So this will attack here and add the bromine on the back side, and that puts this bromine, and then this bond will break. Let's see. Yeah, we form the bond here with the bromine, and then this one breaks and neutralizes that positive charge. And now we get a bromine on this side, and we get a bromine on this side. Excuse me, that's right. That's not right. It's on the back side. There we go. And that leaves this methyl group pointing out, and this one in the plane. Okay, so that was just a rehash of what we studied already. But I thought it bore repeating. Now, if we want to, in the second one, if we want to form a bromohydrin, then, excuse me, the starting material needs to be another alkene. But I left one thing out of that first one. The bromine that we add in the first example must have an aprotic solvent. Whereas in the second example, the bromohydrin formation, we use a bromine. Let's see. Let's write it as a synthesis. Okay. So this is going to be a synthesis, and the well, let's see. This is a single step. We're going to have bromine, and we're also going to have water as our solvent. So what that does is it gives us a bromine on one side from a front side attack to form the bromonium ion. And then water attacks from the backside and leaves us with the hydroxyl. All right, so the difference between the two is that the first one occurred in an aprotic solvent and the second one occurred with water as a solvent. For the last one, if we want chloride substitutions on every carbon, the excuse me. If we want bromine substitutions on every carbon here, if we want a chlorine there and a chlorine here and a chlorine there and chlorine there, then in order to do that, it's going to take more than one pi bond. And we're going to need an alkyne rather than alkene. If we only had an alkene, then we get a anti-addition of bromine across that double bond. But if we have an excess of chlorine in the solution, in the mixture, then, and we have well, I said an excess. If we have an excess of chlorine, then it's going to add across one pi bond, and then it's going to go ahead and add across the other pi bond, which will give us all the chlorine. So in order to do that, we have to start with an alkyne. So that's why we would need this as our starting material, as our substrate. Right there. So that we can add across one and then add across the other. All right, I probably should have called that up to begin with. It'd have been easier to explain. So, if we're still talking about the first example there, where we're adding bromine across a double bond, then they're going to be anti on the addition on the alkene. Whether it's bromine in this case, in the first case, or chlorine, as long as the solvent is non-nucleophilic. So we're talking about an aprotic solvent. If we have a protic solvent like water, then it becomes a strong enough nucleophile that it will complete the SN2 step of the reaction. The electrophilic addition is the formation of the bromonium ion or the chloronium ion. And then the SN2 reaction comes in and releases the first bromine from one side. And that requires a nucleophilic, which is the bromine anion in our first example. And in our second example, the water becomes the nucleophile to attack the other carbon, one of the carbons on the bromonium ion. The bromonium ion. So when it does that because it's water's a fairly good nucleophile, but it's also in abundance. There's much more water there available to bond with the other carbon and release the bromine than there is bromine ion to compete with it. So the water outcompetes the bromine ion simply because there's more of it. And then the last one, we get this tetrahalide as long as there is excess chloride or halide of any kind, typically chlorides or bromides. We learned earlier that fluoride is dangerous to use. The reaction is far too explosive. And then the iodide addition is unfavorable. So we're left with bromine, molecular bromine and molecular chlorine. All right, let's move to the next slide before I run out of breath. Okay. So if we want to do a synthesis where we have, we form an alcohol on the more substituted carbon, then our best choice would be an alkene. This is a terminal alkene using oxymercuration reduction. Well, let me see. I'm going to flip back. Let's see. That's the boron part. Oxymercuration should be way, way back here. I'm sorry. Let's see. Oxymercuration with reduction. Okay. So the mechanism is going to be, well, I thought it was going to show us a mechanism. Maybe we have to go back further. Here we go. This is our oxymercuration. And you'll see that the double, this is the terminal alkene, and the electron-rich pi bond attacks the mercury, but in order to maintain the octet on this terminal carbon, it also forms a bond with the mercury. So we get this three-membered ring with mercury positively charged and in the ring. And what that does is the largest positive charge is going to be on the more substituted carbon. Well, the one reason I can think of is that these methyl groups have an electron withdrawing character. So it makes it slightly more positive than this one. They're both positive, but this one is a little more positive. So the water then in SN2 step goes in and forms a bond here and releases the mercury from that side. And then we need a proton transfer back to a water molecule. And that leaves us with the hydroxide on the more alkyl substituted. In this case, it's a secondary carbon. Right. And then the sodium borohydride goes through several reduction steps that we're not going, that the author chose not to show us because it was way too complicated. But what this step does, what these multiple steps do in the process, is they jumble up the stereochemistry, right? So we get a whole mixture of stereoisomers in this process. But we do end up with the hydroxide on the secondary carbon rather than on the primary carbon. All right, so now let's go back to the slide that we were on before. Let's see. We're getting there. Here we go. Okay. All right, so we learned about two reactions that add water across an alkene or an alkyne, double bond or a triple bond. And those reactions were one, the oxymercuration reduction, which I showed you just a second ago. Another one is hydroboration oxidation. And we have two examples of the oxymercuration reaction. And the first one is oxymercuration reduction across a double bond. And the second example here is oxymercuration across a triple bond. And these are both terminal. terminal double bond, terminal triple bond, terminal alkene, terminal alkyne. And initially, the alkyne is added. We get the hydroxyl added to this second carbon, but since it produces an enol, which is unstable, very unstable, it tautomerizes into a ketone. So when you run this procedure on an alkyne, the oxymercuration reduction will give you a ketone rather than an alcohol. Now, if we want an alcohol across a double bond, then we can also use hydroboration and oxidation. And this oxidation is different. It's not sodium borohydride. It's hydrogen peroxide in basic aqueous solution. And this gives us the alcohol and the hydrogen in syn addition. In other words, they add to the same side. And that's because of the way the borane adds across the bond in a single step. So it comes in from one side and it stays on that side. So that the hydrogen that is left on one carbon is on the same side of the molecule as the hydroxide that's left after the process of reduction. And the reduction in this case is stereospecific. So it doesn't jumble up like the oxymercuration, the sodium borohydride step jumbles up the stereochemistry, whereas the hydrogen peroxide doesn't do that. So you have an established stereochemistry. Now, when we do this to an alkyne, we still have to tautomerize the hydroxyl because it produces an enol. But the process of hydroboration leaves a hydroxyl on the terminal carbon, the less substituted one. And when it tautomerizes, that leaves you with an aldehyde rather than a ketone. Okay. Yeah, go back and look at the flip back and go look at the earlier discussion of the hydroboration and oxidation across the alkyne. All right, I left that comment out. This oxymercuration is a Markovnikov addition. That's why the alcohol results, the alcohol is left on the more alkyl substituted carbon, and the hydrogens are added to the more hydrogen substituted carbon. That would leave it as a Markovnikov addition. The hydroboration, though, gives you an anti-Markovnikov regiochemistry because of the way that the boron, the borane, connects to the carbons that were once double bonded. And in addition to that, we don't just get one borane, we get a triborane, right? You get 3 of these molecules attached to that borane, and then we have to do 3 oxidation steps to free them up. But they give you an anti-Markovnikov, which puts the hydroxyl on the terminal carbon, whereas in the Markovnikov, that's where the hydrogens will go. All right. So now let's look at organic syntheses involving just simply adding hydrogen across the double bond. This is not, strictly speaking, a electrophilic addition, although it bears some resemblance to it. But it's put in here simply because there's no better place to put it. So this discussion of hydrogenation of alkenes and alkynes is a good place to put it, is right here in our electrophilic addition discussion. So what do? Well, in the process of hydrogenation of an alkene, we simply need molecular hydrogen, gaseous molecular hydrogen, which is bubbled through the reaction mixture under 1 atmosphere pressure. So it's coming in very slowly. And then we need a catalyst, a metal catalyst, either platinum or palladium or nickel. Any one of those will do. And they're all in the same group, excuse me, of transition metals. They're all in the same column. And we need this in aqueous solution. And the solid catalyst, the palladium, platinum, or nickel, needs to be very finely divided. Need lots of surface area, because this chemistry takes place on the surface of the metal. And we're going to show you that in just a second. And what we do is we convert that double bond to a single bond and add hydrogens to it. I think I mentioned earlier, when we talked about tetrahydrofuran stabilizing the borane molecule. Well, tetrahydrofuran is this molecule. Oops. Let's try that again. Like that. Furan has a double bond here and double bond here. So all we have to do is remove that and put a hydrogen here and a hydrogen there, and remove that and put a hydrogen here and a hydrogen there. That's tetrahydrofuran. And we have added hydrogen across that double bond. Now, one way to do it is simply hydrogenate it with this method. That may not be the method of choice, but it should work. All right, so and the efficiency is reasonably high, 80% or better, at least in this example. All right, so there's the black and white of it. It's a very useful reaction in syntheses. All right, so the green spheres represent the catalyst. And what happens first in step 1 is our proposed mechanism. Is step 1, hydrogen is adsorbed, not absorbed, but adsorbed, which means it's a surface phenomenon. It happens at the surface. It's not like absorbing water into a sponge. This process takes place on the surface of the metal. So we adsorb hydrogen to the surface, and the bond between the hydrogens is broken and forms some type of association. We're not sure what kind of bond it is, but the hydrogen is associated some way with the catalyst atoms. Okay. Second, the alkene is now absorbed by means of the carbon atoms to the surface of the metal. Then in step 3, we get the formation of hydrogen-carbon bond, and simultaneously, when that bond forms, both the hydrogen and the carbon are released from the catalyst. They no longer are bound to the catalyst, but the other carbon and any hydrogen nearby are still bound to the catalyst. Well, that they quickly form, because now that carbon is, let's see, 1, 2, 3. Yeah, it's, well, let me see. That carbon that's still bound, well, approaching it in our standard format doesn't seem to work very well for me. So we simply form a bond between another hydrogen and that carbon now that it's, the electrons should be available somehow. If we form a bond between the hydrogen, because when the bond breaks for these hydrogens on that surface, right, and you have a hydrogen here and a hydrogen here, the bond that was here now is here and here. That means that this is essentially a free radical, right? Because there were 2 electrons in the bond between the 2. And the association is sort of nebulous. I don't fully understand it. I don't think most scientists do either. But then when you get the carbon, you get the carbon we're starting to break this pi bond when we form that association. So we've weakened the pi bond. We've actually broken this bond, and now we have a weak association here. Now the one electron that's spread over here and the other electron that's spread over here gets together with this electron, and that's where you form that bond and break this one, right? So then you do the same thing over here on this side, and we have completely severed the pi bond. Now we have 2 sigma bonds, one with 1 hydrogen on one side and the hydrogen on the other side. That's the way I see it. And as a consequence, these hydrogens are added in syn fashion, that is, on the same side of the carbon-carbon. Okay, so it preserves the arrangement of these methyl groups. In this example, we have methyl groups bound to these carbons. So these methyl groups here are in the same relationship after the reaction as they were before. So we preserve the stereochemistry in this process because the hydrogens are added in syn fashion. Now, this is known as a heterogeneous catalyst. And for those of you who have had my CHEM112 class, second semester chemistry, we discussed catalysts there. And heterogeneous catalysts occur in a different phase than one or more of the reactants and the mixture of whatever the case may be. In this case, we have all 3 phases represented. We have a solid catalyst. We have a liquid solution of the substrate, the alkene, and we also have a gas being introduced as hydrogen gas is being bubbled through this system, and it's constantly agitated. Let's see. So that's a heterogeneous catalyst. In other words, it's in a different phase than any of the reactants. Okay, these are the steps that I just described to you in black and white. So I'll just scroll through these. Okay. And then we finish off and release the molecule from the metal. I will say, though, add this last statement. The reaction rate, since it occurs at the surface of the catalyst, the more surface area you have, the faster the reaction. So if you want a fast reaction, then you want your catalyst to be very, very finely divided, very small particle size. It gives you lots of surface area, and that will speed up the reaction. All right. So what happens when we try to hydrogenate an alkyne? Well, you can hydrogenate in the fashion that we showed earlier. In other words, these two blue hydrogens are added syn fashion on the same side of the triple bond, and we're left with one pi bond. And that requires one equivalent of hydrogen for each equivalent of alkyne. So that's one way to help limit the reaction, is to limit the reactants. The hydrogen is limited by how much is there. But if we have excess hydrogen with one of these catalysts, then we're going to catalyze further hydrogenation to where we completely remove all the pi bonds. And now we only have sigma bonds with complete hydrogenation. All right. Now, suppose you only want to partially hydrogenate this alkyne. Well, if you've got an excess hydrogen, then it's kind of tricky to introduce equimolar amounts of hydrogen gas with this alkyne because you're bubbling it in there. So it's really difficult to control the amount. So what you need to do, rather than control the amount of hydrogen coming in, control the activity of the catalyst. So we do that by using a catalyst that has been poisoned. In other words, the catalyst activity has been reduced by a process called poisoning. So we inactivate large portions of the surface of the catalyst, right? And that comes on the next slide. One example is this Lindar catalyst. You treat the catalyst in such a way that it slows down the reaction. Based upon our previous discussion, you could, rather than very finely divide the catalyst, you could use large particle sizes. That would slow it down because you would have a smaller surface area, but still that's not enough, because eventually you're going to get full hydrogenation unless you poison the catalyst. And we do that in this case. This is one example, not the only example, but one, where we take palladium and we deposit it on calcium carbonate matrix. And then we treat it with quinoline, this compound right here, and a lead salt. And that really, really slows down the reaction. So you can, it's easier to control how far the reaction proceeds. And I assume that the recipe changes depending on the alkyne that you're using and the type of catalyst you're using. All right, so that's a little beyond our discussion here, but you do get control and can produce a partially hydrogenated molecule. Okay. This hydrogenation is stereospecific, right? In other words, when the hydrogens are added across that triple bond, they are added in cis fashion. In other words, both hydrogens are added on the same side of the molecule. And we see, here's a different, let's see, barium sulfate. This is a slightly different catalyst, palladium with barium sulfate and quinoline again. Then the Lindar catalyst is an example there.
And let's see, what do we have here? We have, if we're going to use this benzyl bromide to produce the other molecule, what we want to look at first is what's the carbon skeleton? Did we change the number of carbons bound together? And yes, we did. We have this benzyl group, and that's the last carbon there. So we're going to have to, in retrosynthesis fashion, we would split it right here and say, what did it take to form that bond? Right? We need a 1, 2, 3, 4, 5, 6 carbon chain. And we need something that will allow us to form the linkage between the end of this carbon chain and this benzyl carbon. Right? So if we do that, right, if we want to break that bond in retrosynthesis fashion, and we start with this one, what can we use to form the rest of those bonds? Well, it needs to be cis, right? So in order to form that cis, we need catalytic hydrogenation of an alkyne. So if we were to start with this alkyne, right, now we have, do we have the right number of carbons? 1, 2, 3, 4, 5, 6. Yes, we have the right number of carbons, and we formed a bond between this benzyl carbon and the terminal carbon of this alkyne, right? So once we get that formed, then we can catalytically hydrogenate it and get the cis isomer, because that's what we're looking for here. We want this this Z isomer. All right, so if we keep going backwards, right, how do we form that bond? Well, if we have this alkyne and we can add it to this bromide, because that's the reactant that we were given, right? We form that bond there with that alkyne. How do we do that? Well, what we need to do first is to use this sodium azide, right, which will activate the alkyne so that now it will, in an SN2 fashion, substitute for the bromide. In other words, we're going to use a nucleophilic attack. So this needs to be negatively charged here, and we do that with this sodium azide, right? And you can go back and look at the previous examples. This would be in chapter 12. I think it's chapter 12. It might not be chapter 12. It might be an earlier discussion of an SN2 reaction. Yeah, it might be an earlier one. So this carbon has 1, 2, 3, right? And then we go 1, 2, 3, 4, 5, 6. Yes. So the sodium azide is presented as this. Oh, excuse me, sodium amide. Pardon me. That's not azide. Sodium amide. So when we break the bond of the sodium is positive and this one's negative. Right? So we have, let's see, 1, 2, 2, 4. Let's see, nitrogen is 5. So we need 5 minus, we need 6 electrons. 2, 1, 2, 3, 4, 5, 6. Okay, there we go. So that's the reactive species. And there's a hydrogen here. And what it does is it attacks that hydrogen. Those electrons are left on this carbon. And this forms the
ammonia molecule. And now we have our reactive species right there.
Okay, so now this is the nucleophile, and it attacks the more positively, well, it attacks the carbon to which the bromine is attached.
Right. So if you have the phenyl group, and I'm going to abbreviate this phenyl, excuse me, phenyl group attached to a carbon and then to a bromine. So we have two hydrogens there. Then this attacks that carbon. Those go over here. It releases the bromine is the leaving group and forms a bond. So now we got a bond right here between this benzyl group and the alkyne. Then what we want to do is reduce it. Right? So if we reduce it in syn fashion, all we need is to selectively reduce, add hydrogen, excuse me, not reduce, hydrogenate these two carbons on that alkyne in syn fashion, and that will produce the Z isomer. Okay. All right. And that's the end of chapter 13.